this event for giving me the honor of coming here and presenting my results in what is undoubtedly the most prestigious scientific event in India. So, as the chairman just announced, my name is Sushil and I'm the principal investigator at an office and microscopic office laboratory in Tirupati, Mumbai. And our lab basically deals with what we now call microscopic optics in resolve. As I go along, I'll explain to you terms such as random lasers, Anderson operation, and I should make one small disclaimer. When I was discussing with friends as to what the audience will comprise of, I'm sure there should be even college students and BSc students, so keep the language a little more amenable. So the experts among you, if you feel far too elementary, I'm sorry about that. So, let me first begin with acknowledging the people who actually did the hard work. You see here Anjani Kumar Tiwari and Ravi Tejas, who are my ex-PhD students. Ranjit Kumar is a PhD student who is currently working on this. And Shara Kali is an ex-postdoc fellow who is now a faculty in ISL Trivandrum. And Shriman is a scientific assistant in my lab. We get funding from Department of Atomic Energy to the office of TIFR Mumbai. And DST has been kind enough to offer the Ramanujan Fellowship and currently the Swaranjanti Fellowship, which helps us in our research. Before going on the term of random lasers, let me just recap to myself what is a normal conventional laser? How does it work? So most of us are probably already aware of it. So the normal laser is going to consist of two mirrors at least two mirrors who are facing each other. And between the two mirrors, there is an amplifying medium, the material which actually increases the energy of light. And this amplifying medium will be pumped with a source of pump energy. So there is an energy source which is pumping this medium, and the amplifying medium will start releasing its light in the form of the laser. We all know that the laser doesn't start blazing immediately as soon as the pump is on. For some amount of pump power, the power is lost in overcoming losses of the resonator of the structure. So till that time, the laser emission does not start. It's only when the losses are overcome by the gain, then the laser emission starts and you start seeing the output intensity growing linearly. Okay, this is called the famous threshold behavior. The threshold behavior is the signature of a laser. Okay, so only when you see this, that's when you can conclude that yes, I have lasing action. And finally, the spectrum of light that comes out of this device looks something like this. You have narrowband emission mode. These are called the laser mode, and these are the function of the two mirrors facing each other, what we technically call a resonator. How does this resonance actually happen? When two mirrors face each other, it turns out that the distance is such that it can sustain a standing wave pattern for certain wavelengths only. Okay, and that wavelength shows up as a high transmission peak inside from the transmitters of this resonator. Now, not all resonators are perfect, or other resonators are often non-perfect. So, whenever the loss in a resonator goes up, these peaks start broadening. Okay, as you can see here, for a slightly increased loss, it will be a red colored spectrum here. When the loss is fairly strong, you actually see almost flat transmitters and the wavelength sensitivity of the resonance is gone. Now, let me take the same physics into a completely unusual scenario. I'll explain to you what I mean. Here's the structure that you see on your screen. Okay, I cannot address this screen to the corners here, but you're seeing a structure of white dots on a black background. Assume that the white dots are small particles of a dielectric, some dielectric with some refractive index, and the black background is air. So, because of the refractive index contrast, every particle will scatter light. Correct? Now, if I inject a pulse of light in the middle of this structure, and if the dielectric contrast is strong enough, then the light does this. This is a two-dimensional computation. What the light is doing is it is trying to escape this whole structure in all directions, but whichever direction it goes, the disorder, the structure will reflect it back into the same direction. So eventually, in principle, the light is trapped there forever. In principle, forever. This is what is known as the localized mode of this structure. It is essentially a resonance, similar to this resonance between two mirrors, essentially a resonance of the disorder structure. It's called a localized mode. Now, if I reduce the refractive index contrast of these particles, okay, this is what light does. I injected the same pulse in the middle, but now the scattering is not strong. So the light actually manages to escape outside. And when it escapes, it undergoes what is known as diffusion of light. You all heard the term diffusion. If I have a spray, a perfume spray, and I spray it in that direction, the person sitting there will also get the fragrance, because over time, the molecules of the spray will diffuse through the room in all directions. That's what the light is doing. It is diffusing in all directions, and the exciting part here is the light obeys the diffusion equation. Okay, in short, the strong disorder gave me a localized mode, gave me a diffusive mode. Okay, that's the technical language. To put it into some amount of parametric number, it is all decided by the comparison of the wavelength of light and the separation between your particles. If the separation is there, if the wavelength of light compares to the separation of the particles, you will end up getting a localized mode. If the wavelength of light is smaller than the separation between particles, you will end up getting the diffusion mode. Okay. Now, This physics, like most physics that we learn, is dependent on the dimensionality of the system. For lower dimensions like 1D and 2D, it is very likely to find the localized mode. I must repeat, likely, not easy. It is easier than in 3 dimensions, but not at all easy by all means. In 3 dimensions, of course, it is very, very hard to get a localized mode. Okay, so a recap: a strong disorder, localized mode; weak disorder, diffusion mode. Okay, this is where random lasing comes. I told you earlier that if you had a resonator and if you put an amplifying medium in there, you get lasing emission. So Letakov, Russia, worked out a theoretical long back. If I have a disordered medium and I embed it inside an amplifying medium, I will get an effect similar to a real laser. The threshold behavior that your real laser shows will also be shown by this structure. For some time there was some amount of rudimentary activity, but in 1994, this paper by Lavandi, it managed to attract the attention of the whole world. Because he experimentally showed what Letakov had theoretically proposed. He said, look, indeed, I do see a threshold from a random laser. Okay. Over the next few years, in which we also had a contribution, we showed that the emission can also have not only a high intensity, but also temporal coherence. So this phenomenon has now taken again a lot of strength as random lasing, coherent random lasing. Okay. And our lab dedicates part of its time in this phenomenon. Now I come to some part of my results. Mr. Chairman, I would request you to give me 5-minute warning. Okay, 5-minute warning. So what do I propose to talk here now? I'll tell you our work on random lasing, one in the case of diffusion of light, which is weak disorder, and one in the case of localization of light, which is strong disorder. Okay. So remember, this is what the diffuse mode does, this is what the localized mode does. So let's start off with the diffusion of light. The topic of this result is basically intensity fluctuations from this system, and it will go on to something called Levy sums, which I will explain. So what is happening here is I have a certain random lasing device, a scenario, and I'm pumping energy to it pulse after pulse. Every pulse which is emitted has a fluctuating intensity. So that's called randomness. So what does the intensity look like? The distribution look like? So you see something interesting here. You can all see on your screens the blue, red, and the black plots. These are basically plotting several intensity values with pulse number or spectrum number at a given wavelength. You clearly see a difference between the black and the red one. In the black one, I can kind of estimate that there is a limit on the maximum intensity I get, but in the red one, you can never estimate the maximum intensity. Okay? Because if I draw a line, if I say that, look, after this point here, this is the maximum intensity, but I get a pulse here which is even higher. And if I had done the experiment for 10,000 pulses, I might have gotten a pulse which is even higher. So you can never confirm that this is the maximum intensity the system will emit. This technically is called diverging variance, diverging moment, a classic signature of what we call power law distribution. Most of us are aware of, acquainted with Gaussian distribution. They are the most commonly occurring distribution. Power law distribution is a completely different distribution. If I told you that I have a Gaussian distribution with a mean of 50, okay, then you know that you will have values like 60, 70 or maybe 80, but you will never have a value up to 10,000. That's not possible. With power law, with Levy statistics, you can't put a scale on the value. It can have any value. Okay, and that is exactly what this plot is showing. Okay, so and a power law is seen to the students here to identify a power law. You plot your distribution on a log-log scale, it looks like a straight line. This is experimental data which shows up as straight. Okay. So this was measured. What we did first was, we got this intensity distributions, and I have to go very fast here, so I'm leaving out the details. We basically gave this red line fit to our community. It was borrowed from financial physics. This red line fit gives out a certain parameter called alpha. You can see it in the bottom left of the screen. Alpha 2 implies a Gaussian distribution. Alpha less than 2 implies a power law. Okay, or a Levy statistic. And how far alpha is from 2 describes how much strong the power law fraction is. Okay, so now what this did was, it gave us a quantifiable parameter to describe the statistic. Now we construct a map. So on the x-axis of this map, you can see the pump energy of the random laser is varying. On the y-axis, which is not labeled here though, it is the disorder strength, and these three numbers L indicate the sample size. And the color of this point here tells you what the alpha is. So red color says alpha equals 2. All these regions which are Gaussian, and blue color says strong Levy, so in the middle region. You can see some trending changes with sample size. This is the map of how a random laser intensity will behave under varying disorder parameters. Okay, we went ahead to the theory of this. I will cut a long story short, but I should refer to this very, very beautiful paper called the truncated Levy flight. Like I told you, the power law doesn't have any scale, so in principle infinite is an allowed value. But real world doesn't have infinities, right? So the statistics community was uncomfortable with this situation where we have infinities in our treatment. So Mantegna and Stanley proposed this concept of truncated Levy flight. So they said that based on your physical situation, you start proposing truncation of high values in a particular manner, and then your system will come back to finite moments or towards a Gaussian. Okay. So here is the number. If I have an untruncated power law, okay, the value of alpha is 1.16, but the same distribution with truncation will tend to a Gaussian of 1.9. So when we decided to map the energy process onto the truncated, right? So here is the straight line power law behavior, and then we found that indeed there's a truncation on high values. It doesn't come finitely like that, but very soon it starts dropping. The large values are dropping. Okay. So what we did is we estimated some parameters. Important ones are basically this power law exponent mu and this beta exponential minus beta, which truncates the high values. Okay. So following a certain parameter estimation routine, we actually found out what those values could be at a given disorder strength and a given pump energy. Once we had that, we mapped it onto a truncated Levy sum process. Details you can ask me later, and that is the agreement with the experiment. This is the computed map, this is the experimental map, and you will agree that this fit is absolutely perfect. Very beautiful fit here. And what we have done here is a single platform on a single explanation of exponentially truncated Levy sums. We have managed to explain the intensity behavior of the random laser on all variation of intense pump energy and variation of disorder strength. And so this result took a lot of attention from my community. I don't know if this crowd is aware of physical revelators. Students may not be. So these are some journals which are very highly regarded in our community, the physics community. So we managed to get there in the last year. Now, the next part of the talk. How much time do I have? At least 7-8 minutes. Oh, 9 minutes. Thanks. The next part, the last part of my talk, I just covered diffusion for you, and we discussed Levy sum. I will now go to the strong disorder, which is localization. Remember that when the disorder is strong, you can get localized modes, which are resonant modes of the system. At this point, you have an interesting point. Okay, when I say let me make a random system, there are two ways of doing it. One is take a bunch of particles, put them together. It will make a random system. The other one, which is a cleverer one, is the following. First, start with the periodic arrangement of particles, which is see on the left of your screen, and start displacing each particle by a tiny amount in a random way. Okay, so that displaced particles is not periodic anymore because you have displaced it deliberately. But on the average, it looks periodic. The second one is actually random because I made it first. And you can see that in the part, the displacements are stronger. You can see that this is random, but on the average, it is still periodic. This is called a periodic on average randomness. So why do we do this? The idea is it is known that periodic systems can sustain good resonances, and by making them gradually random, you are coaxing that resonance into the disorder system. So basically, you are allowing a mode, the localized mode, to slowly being formed by going from periodic to a random, periodic on average random. And this is what we have achieved experimentally recently in 1D. How did we do that? We'll use the perfume bottle. When you spray it, it forms lots of droplets. Okay. So we have a small microcapillary which has a certain device onto it. What it does is it creates micro droplets, but they are all exactly of the same size and separation. I don't know if you can see the contrast. There are red micro droplets separated exactly by the same size all over. This is a periodic one-dimensional array. This is our periodic one-dimensional. I can change the performance of this device and get this kind of a configuration where I see these droplets which are all of the same size, but the separations are now random. Okay, this is the periodic on average random configuration which I was referring to. Finally, if I wanted, I could just get a completely random structure where the sizes are also random and separations are also random. So this device helps me from going from periodic to randomness in a graded fashion. Now, if I look at the spectrum, so this is your array. I'm pumping light to it like in a laser, and I'm seeing the spectrum at the end of it. If I look at the spectrum in this system, you see these peaks which are random, but you cannot predict them because every configuration will give you a different position. But overall, it follows a certain law. Okay, you can see the positions of these wavelengths. If I plot them as a histogram, they have allowed and forbidden band. You cannot have a peak at this point, for example. You can have peak only in this red band. This was an interesting experiment. Okay, when we did the theory of this using something called transfer matrix method, it's a one-dimensional method. Details later if you are interested. We could explain exactly where these peaks are coming from. Okay, here is again the comparison between the theory, which is on the left side of the screen, and experiment on the right side. The topmost plot shows you a continuous distribution for a completely random system, which matches exactly with this continuous in the bottom of right. Okay, and in the middle plot, compare these numbers, separations 4.9, 4.5 nanometers with the blue plot. Again 4.9, 4.7 nanometers. Bottom one is I guess 6.9 nanometers, which compares to this red histogram. Okay, these numbers are perfectly matching. Based on these conclusions, we could basically tell the world that look, what we are observing, random lasing over gap states from a quasi one-dimensional amplifying periodic on average. I have emphasized the term gap states. Most of you have studied solid state physics. You have learned of conduction bands and valency bands and the band gap in between, right? 5 minutes? Perfect. And the band gap in between. this is exactly the same band gap that this gap state is referring to. The randomness in this periodic system created new states in the band gap of your earlier crystal, and that is the state which is lazy. Okay, this was another important one because the community needed to have a sample which conclusively gives you a gap state. Okay, so we managed to get into PRL here also. But what is really exciting about gap states is this: gap states and localization are very intimately connected. It turns out that if you look at the properties of localization, then almost always, your gap states will be strongly localized. They will be resonances of your system. Okay, and to know how do you confirm it to yourself? Let's consider this computation here. There are two peaks I've shown and marked with colored arrows. You have to look at the spatial light intensity distribution inside the structure. What I mean is, this is the structure. How does the light sit? Is there maximum here? Is there maximum here? How does it sit? Okay, and the computation gives you results like that, like this one here, for instance. The red arrow here indicates this mode. You can see a clean exponential decay in both the wings. This exponential decay is a classic signature for strongly localized mode. Okay, so you have to see this to say, yes, I am absolutely seeing localized mode. The log scale, you know that the exponential decay shows up as a straight line, and you can see this quantifying by the straight lines in the two wings. The peak can be anywhere. You cannot predict that because it is random. But even the other mode, although it is separate in peak, has an exponential decay. So this kind of spatial intensity profile is what we were looking for. We devised an experiment which will measure that kind of an intensity profile, and the experimental results fall perfectly in place. You can see these two are experimental modes now. What you saw earlier was theory. And you can see a clean exponential both the wings, straight line in the analog scale. So we have identified here what is, to my knowledge, the first time direct observation of random lasing over the localized states, also known as Anderson states. Okay, forget the name. But this is the first experimental demonstration of exponentially decaying photon wave functions in Anderson states. We haven't stopped there. Last slide. We've gone ahead and used a device called the streak camera. Some of you will know a streak camera is a very high temporal resolution device, 2 picoseconds, up to 2 picoseconds. And we have measured the lifetimes of these modes. The first measurement is to conclusively show Anderson, the localized mode, and then see how long it lives. And here's the answer. Here, this is, I would call, let's say, strong disorder. Okay, these terms are used a little loosely. Okay, strong disorder and weak disorder. And you can see that these are the pulses, temporal profile of these pulses coming out. And here's the histogram of the lifetime. You see a single peak skewed distribution, left skewed distribution. But when I make the randomness very, very small, so it is more periodic in that sense, I see a double profile. Okay. This was the experimental observation. We went ahead and did the theory, which I will explain to someone if you are interested. And that actually matches perfectly again. This is our theoretical result. In slightly random systems, more random systems, you see a single peak distribution. But in more periodic systems, you do end up seeing multi-peak or dual peak distribution. So what this is actually is another direct measurement of lifetimes of Anderson localized lasing states. And that's what I wanted to say with you today. These are the conclusions for those who are interested, and these are some of the references that will cover most of this. Thank you for listening.